So in this lecture, we are going to derive analytical expressions for time domain specifications. Please remember that we are talking about second order systems, right? Of the form k omega n square, s square plus twice zeta omega n s plus omega n square. These are second order systems without a zero. And we have been talking lately about time domain specifications of a particular class of this response, which is the underdamped response, which happens underdamped response to step input, right? Which happens when the quantity zeta here, which is the damping ratio, is between 0 and 1. So zeta lies between 0 and 1. Now, in the last lecture, we discussed about the time response specifications and the definitions. We talked about four quantities: the peak time, the rise time, the settling time, and the percent overshoot. So today, after these definitions have been clearly understood, we can find out analytical expressions for these four quantities. Okay, so let us start with what was the step response that we actually found. So the step response that we derived after taking the Laplace inverse of Cs is given by this expression: Ct is equal to 1 minus exponential minus zeta omega n t cos omega dt plus zeta upon under root of 1 minus zeta square sin omega dt. Here omega d is equal to the damped natural frequency, which is omega n into 1 minus zeta square. So this response can be written in two ways to simplify it. So you can either, in order to obtain just one trigonometric expression inside the bracket, you can write this thing inside the bracket as cos r cos phi cos omega dt plus r sin phi sin omega dt, where you have basically substituted uh, r cos phi as 1 and r sin phi as zeta upon under root of 1 minus zeta square. When you do this, you should be right. You will be able to write inside as r. So this is cos a cos b plus sin a sin b. You can write this as cos omega dt plus phi. So the whole expression becomes Ct is equal to 1 minus exponential minus zeta omega nt into r. We can take the r outside, and inside we can write cos omega dt plus phi. And the value for r we can obtain from these two substitutions that we have made. So since r cos phi is equal to 1 and r sin phi is equal to zeta upon under root of 1 minus zeta square, we can square and add these two terms. You'll get r square on the left hand side, and on the right hand side you get 1 plus zeta upon under root of 1 minus zeta square whole square, which gives you 1 upon 1 minus zeta square. And you can write your r as 1 minus exponential minus zeta omega nt, and your r is actually under root of 1 minus zeta square from here. And inside this phi, cos omega dt plus phi that you have written, this expression has a k outside. Yeah, I forgot to write this k. So because the second order transfer function has a gain k, so this Ct is equal to k times this, and phi would be, you can take the ratio of these two quantities. So you have tan phi is equal to zeta upon under root of 1 minus zeta square. So this is cos a cos a cos b plus sin a sin b, which is cos a minus b. So this is your expression. So we have been using this expression before, and it is basically derived from the original expression that we obtained earlier. So the second order response can be written like this, right? where Ct is equal to k times 1 minus exponential minus zeta omega nt divided by under root of 1 minus zeta square cos omega t minus phi, and phi is basically defined as tan of under root of 1 minus zeta divided by under root of 1 minus zeta square. You can also write this expression inside. Instead of writing it as cos A cos B sin A sin B, you can write this as uh, cos A sin A cos B plus cos A sin B, right? In that case, the substitution that you will make, in that case, this thing in bracket, so this expression in the bracket you're replacing by, so you're writing sin phi and cos phi. So you're replacing it like this, and your r sin phi would be equal to 1, and r cos phi would be equal to zeta upon under root of 1 minus zeta square. So in case you do this substitution, you'll get a slightly different expression, which is going to be k 1 minus exponential minus zeta omega nt divided by under root of 1 minus zeta square, and instead inside you'll get sine, because you are writing this as sine A sine B plus cos A sine B. So this is sine A plus B. So inside you'll get sine omega dt plus phi, and in this case your phi would be, your tan phi would be the reciprocal of the tan phi that you obtained here, will be 1 minus zeta square by zeta. So these are two expressions for the same response. In fact, three expressions in total now, but basically these are different ways of saying the same thing. Why I derived this was because our expression for rise time is actually derived using this expression here. So how is it derived? So basically you have two definitions for the rise time, if you remember. So rise time, what is the analytical expression? So we have two definitions for rise time. One is the 0 to 90% definition. The other, the 10 to 90% definition. The other is the 0 to 100% definition. Now we'll derive the expression for the 0 to 100% definition of the rise time using this expression. The derivation of 10 to 90% is definition of rise time is not analytically possible, right? So we don't use analytical means to derive the expression for this. We have to use numerical methods, but this can be done using analytical methods. So since our CT is given by the expression here that we have to see when is CT going to be equal to K. When is it going to be equal to K, right? So it is going to be equal to K for the first time. That is the time, right? When CT is equal to K, we'll call it the rise time, because uh, our 0 to 100% definition of rise time is that the time that it takes for the waveform to reach from 0 to the steady state for the first time, the steady state value for the first time. So this is the rise time, the 0 to 100% definition. So this term will be equal to K for the first time when this thing inside becomes 0, right? Because 1 minus, when you equate the CT equal to K, this is possible. It is possible. Okay, let us do it. So we have this K 1 minus exponential minus zeta omega nt under root of 1 minus zeta square, and inside we have sine omega dt plus phi. This should be equal to K, and this is going to be possible if we cancel this K out, and you have 1 on the right hand side. You subtract this one from this one here. You have exponential minus zeta omega nt under root of 1 minus zeta square sine omega dt plus phi. This has to be equal to 0. And this is going to be 0 not when the exponential is 0, because the exponential is going to be 0 at a fairly later time. when time is close to infinity from the expression. So this is going to be 0 when the sine omega dt plus phi is equal to 0, right? And this is going to be 0 for the first time when this angle is equal to phi. So omega dt plus phi is equal to pi. That means this t is equal to pi minus phi divided by omega d. This t is the rise time, the 100% rise time, right? 0 to 100% rise time. So the rise time expression is pi minus, now what is this phi? This phi is the phi that we obtained here, right? Tan inverse under root of 1 minus zeta square by zeta divided by omega n under root of 1 minus zeta square, right? Please remember that the Book of Nice does not give this expression for rise time, because there the rise time definition is the time taken to rise from 10 to 90%. But this is given in some other books where the rise time definition that is taken is the time taken from 0 to 100% of the steady state value for the first time. So this is the analytical expression for rise time. We see that it is a function of both omega n as well as zeta. Now let us look at the second important uh, time domain specification, which is the peak time. How do we derive the peak time? So again, the peak time is going to be obtained, right? When you reach you define the peak time as the time required to reach the first peak, the first peak. So this is your peak time, and you have to find the expression for this. Now we find the expression for this by actually looking at the derivative of Ct. The derivative of Ct at this peak is going to be 0. So your C dot T would be equal to 0. So you can find the expression for T peak time from this relationship that you have. Now, instead of differentiating Ct directly, which is going to be slightly cumbersome because Ct has a slightly complicated shape, what we'll do is we'll try to find out C dot T from Laplace inverse of SCS, right? Because when you multiply with S in the frequency domain, you actually differentiate with time in the time domain. So your CS is actually k omega n square s s square plus twice zeta omega n s plus omega n square. We already know this. So SCS is going to be k omega n square s square plus twice zeta omega n s plus omega n square. Now you can find the Laplace inverse of this very easily because we have already derived this. So let us go for the partial fraction expansion if we need it. So we write this as k, and inside we write this as omega n square. We write this as s plus zeta omega n whole square, and then we write the other term as omega d square. This is what we have done before as well. Here your omega d, again let me remind you, is omega n under root of 1 minus zeta square. So this is the case of zeta being between 0 and 1. So the poles are complex, and this is how we have to do the inverse Laplace transformation. So if we take the Laplace inverse of SCS, and from this expression here, the Laplace inverse of this expression, this is going to be k omega n square divided by omega d square, and then inside you will be writing e to the power minus zeta omega n t and sine omega dt, right? Because the Laplace inverse of omega d s plus zeta omega n whole square plus omega d square is going to be this term here. This is omega d, yeah. So the Laplace inverse of this term is going to be this term that you have here. So you have to multiply and divide by omega d, right? Yeah. Okay, so this is okay. Yeah, yeah. So we can write this as uh, k upon under root of, no, not under root of. We can write this as k upon uh, 1 minus zeta square, and inside you have exponent e to the power minus zeta omega nt sine omega dt, right? So do we have, yeah, so we multiply and divide by this. Let me check this expression. Just give me a second. Yeah. Oh, there's one mistake here. So you multiply and divide by omega d. So this is omega d here, and and you basically have, you don't have this expression. You write this as k. So let me rewrite this as, this will be k omega n square. This is going to be omega n under root of 1 minus zeta square. Although this does not have an effect on our derivation, but still to be right. So this is the expression for c dot t, right? So we can simplify this as k omega n under root of 1 minus zeta square. Yeah. And then you have exponential minus zeta omega nt sine omega dt. This is okay. Right. So this is the expression for c dot t. Now, when is this going to reach the peak? What is the peak value? So it's going to reach the peak when this sine omega dt, right? This derivative is equal to 0. So this has to be equal to 0. So this, and this has to be equal to 0. That means this thing here has to be equal to 0, which means that omega dt has to be equal to pi. So the first peak would be obtained at pi. You actually have to write n pi with n is equal to 0, 1, 2. N is equal to 0 will of course give you 0 time, and that is when the derivative is 0, and then the first time that the derivative becomes 0 after 0 time is when t is n is equal to 1. So omega dt is equal to pi. This gives t is equal to pi upon omega d, which is pi upon omega n under root of 1 minus zeta square. Right? So your first peak is going to be obtained, first overshoot is going to be obtained at pi upon omega n under root of 1 minus zeta square. Right? So this is the peak time. You can also find the time for the first undershoot, because once it overshoots, then it will undershoot. This undershoot will happen when n is equal to 2. So you put 2 here, this 2 pi upon omega n under root of 1 minus zeta square will be the time for the first undershoot, right? So, but we are not really interested in this. So we wanted the expression for the peak time. We got the expression by setting the derivative equal to 0. The amplitude here, in which we slightly miscalculated here, does not actually play a role in the derivation, but still, in order to be correct, we had to change it slightly. Now look at the third important character, which is the specification, which is percentage overshoot, right? So the percentage overshoot would be the overshoot at the peak time. Yes. So how much is the overshoot that that takes place when the time is equal to TP? So basically, if you substitute CT and you substitute the time t is equal to TP, you'll get this value, which is the the value of CT at time t is equal to TP, and then from this value you can you can obtain the percentage overshoot. So if you look at this CT t is equal to TP, let us take the expression. We have 1 minus x e to the power minus theta omega n t under root of 1 minus zeta square. Let us take the first expression that we have. No. So this is minus zeta omega n t divided by under root of 1 minus zeta square, and inside you have cos omega dt omega t minus 5. So this is the expression, the first expression that we derived actually. So now we have to substitute t is equal to Tp in this. So when we do that, what do we get? Get k 1 minus, now I'll write this as exponential, easier for me to write, minus zeta omega n. Now I have to substitute this here, this value. So pi divided by under root of 1 minus zeta square, and this whole thing divided by under root of 1 minus zeta square, and inside I have cos. Now omega d into tp, omega d into tp would give me, because omega d is here in the denominator, this will give me pi. So this gives me pi minus, and this phi is tan inverse zeta upon under root of 1 minus zeta square, right? So now I'll simplify this here. So I get this CT at t is equal to TP. This is equal to k times 1 minus exponential minus zeta omega n pi divided by under root of 1 minus zeta square, this whole divided by under root of 1 minus zeta square, and cos pi minus theta I will write as minus cos theta. So minus cos phi. So this is becomes plus, and here I have cos tan inverse zeta upon under root of 1 minus zeta square, right? So this becomes, this thing you can simplify. This thing will be equal to cos of tan inverse theta upon 1 minus zeta square is actually 1 minus zeta square. So you're left with k, and this 1 minus zeta square and this 1 minus zeta square will cancel out. You're left with 1 plus exponential minus theta omega n pi divided by under root of 1 minus zeta square. This is your CT at t is equal to TP. Now the percent overshoot would be CT at t is equal to TP minus the value of CT which at steady state, which is k divided by k. So this is your percent overshoot. Right? When you put this expression here, you can easily see that the percent overshoot is given by exponential. This has to be multiplied with 100, of course. So exponential minus theta omega n pi divided by under root of 1 minus zeta square into 100. So this is your percent overshoot. So one very interesting conclusion of this is that the percent overshoot is only a function of zeta. So percent overshoot is not a function of the other important parameter, which is function of omega n. It is not a function of k. It is a function of only zeta, right? Okay, so this was about the other important parameter, which was the percent overshoot. Now let us take the third one, which is left, which is the settling time, TS. Now for finding settling time, I had actually sketched this waveform that I had shown you in the beginning, right? So what is this? What is this waveform, and why it is required for understanding how to find settling time? Now let us look at Let us first look at the waveform for sine omega t, right? So, so just a second. So this sine omega t I have sketched with in black color. So you can see black is a pure sinusoidal wave. Now, what is going to happen if I multiply sine omega t with exponential and exponentially decaying term? So the second uh, thing that I want to sketch is e to the power minus t sine omega t. Now, e to the power minus t plus and minus I've sketched using the red color. So you can see that this exponentially decaying term, which also starts from 1 and decays to 0, in red color is e to the power minus t, and this the other one here is minus e to the power minus t. Now when you multiply e to the power minus t and minus e to the power minus t, the sorry, when you multiply e to the power minus t and sine omega t, you get e to the power minus t sine omega t, and I have sketched it using blue. Now, how do I sketch it? This is interesting. See, because sine omega t varies between plus 1 and minus 1, e to the power minus t sine omega t actually varies between e to the power plus e to the power minus t and minus e to the power minus t. Why is it that? Because we have to start from, say for example, this point. We start in blue and we have to multiply this 0 with this 1 here, because this red is e to the power minus t, and when we multiply this and this, I get this point back. Now the second point that I want to sketch is I want to multiply this one here, right, on the sine omega curve with this quantity here, which is the envelope e to the power minus t. So I get this point here, right? And then going down, I have this negative peak here, right, here of sine omega t, and I have to multiply this because it's a negative peak. I have to multiply the I have to find the peak here on the minus e to the power minus t curve, right? So my peaks, the location of my peaks would remain unchanged. So my peak is here on the sine omega curve. It is here on the e to the power minus t sine omega curve. My peak is here on the sine omega curve. It is on here on my e to the power minus t sine omega curve, but it is being multiplied by minus t. But what is happening in the negative side is that when my peak is here minus 1, it will be at minus e to the power minus t, because now I'm also multiplying with minus 1. So this tracing these peaks, right, corresponding to a plus peak, I draw a dot on the e to the power plus t minus t curve, and corresponding to a minus peak, I draw a dot on the minus e to the power minus t curve. I get these points here, and when I connect these points, this blue colored waveform that I obtain is the waveform for e to the power minus t sine omega t. Similarly, if I have a more complicated waveform now, which is 1 plus e to the power minus t sine omega t, then I have to shift this whole waveform up by 1. So what I have done here, I have shifted this whole waveform. So this yellow and green that you see is the same curve that I have shifted up by 1. And now I can see that the waveform, earlier my waveform, the blue colored one, e to the power minus t sin omega t, was between two envelopes. Envelope was e to the power minus t and minus e to the power minus t. Now my waveform, which is 1 plus e to the power minus t sin omega t, is between two envelopes. The envelope is 1 plus e to the power minus t, this one, the yellow one here, and the other envelope is 1 minus e to the power minus t, the other yellow one here. So basically, why I did this was to tell you that actually the expression for the underdamped response that we obtain here, we can actually see the envelopes between which the actually the oscillations take place, right? So let me write down, and that is going to help us in finding the peak time. So we wrote the expression like this: k 1 minus exponential minus zeta omega nt under root of 1 minus zeta square, and then inside we have cos omega dt minus phi. I use this expression more often, and my phi is tan inverse zeta divided by under root of 1 minus zeta square. So I can see that, when I could see that 1 plus e to the power minus t sine omega t, and actually this waveform is between two envelopes, which is 1 plus e to the power minus t and 1 minus e to the power minus t. In a similar way, I can see that this expression that I have would be between two envelopes, right? Two exponentially decaying envelopes. So this is my underdamped response, and these are two exponentially decaying envelopes, one from the positive side, one from the negative side. Now this one from the positive side would be obtained by taking the plus sign here. So this one from the positive side, from what our discussion below, would be k 1 plus exponential minus zeta omega nt divided by under root of 1 minus zeta square, right? So this is the expression, this is the envelope from the positive side, and the envelope from the negative side would be k 1 minus exponential minus zeta omega nt divided by under root of 1 minus zeta square. So between these two envelopes, uh, my waveform would be actually oscillating, right? So this helps us in finding the settling time, because uh, we want to find the time when this envelope is actually only 4%, right? Remember the definition? The definition is 98% to 102%, right, of the final value. So when you oscillate between 0.98 of CT to 1.02 of CT, right? That is that when you start oscillating between these two ends, that is the time that you say is your settling time. So basically, the distance between these two envelopes should be equal to 0.04. That is, you're oscillating in the 4% margin. So if you subtract this envelope from this envelope, you should get 0.04 when your settling time starts, right? 0.04 times k, because you're actually uh, the final value is k, right? Between 0.04 value of k. So when you do this, you actually write k times 1 plus exponential minus theta omega nt under root of 1 minus zeta square, right? Minus k times 1 minus exponential minus zeta omega nt under root of 1 minus zeta square. This should be equal to 0.04k, and this gives you, because this 1 and 1 cancel and the k's will cancel out with each other, this actually gives you exponential minus zeta omega nt under root of 1 minus zeta square should be equal to 0.02. So this is the time, this time that you have here is the time when you actually oscillate between plus 2% and minus 2% of your steady state value, right? So you can simplify this and take this as minus theta omega, and I write Tp here is equal to uh, exponential is equal to 0.02 under root of 1 minus zeta square. Take the ln on both sides, get zeta omega, and Tp is equal to um, minus ln 0.02 under root of 1 minus zeta square, and you can write Tp as minus ln 0.02 under root of 1 minus zeta square divided by zeta omega n, right? This expression in the numerator, it is seen that it varies for a variation in zeta from 0.1 to say 0.9, this variation in the numerator is very little and it stays around 4, right? So you approximate TP because your variation in the numerator is not much with variation in zeta between 0 and 1. You approximate TP as 4 by zeta omega n.